Swayam Prabha. Digital India. Educated India.
Good morning. We continue with our discussion on computer-aided engineering design. We have been discussing spline, segments, and curves. A quick recap on what we did last time. We used the Leibniz result to derive the recursion relation for B-spline basis functions. We worked with the divided differences of the product of two functions. Ht equals ft times gt. The kth divided difference of h, which is h within square parenthesis t0, t1 up till tk, is given as summation r going from 0 to k. The rth divided difference of f of t0, t1 up till tr, times g within square parenthesis tr plus 1 up till tk. We can expand this. The expression will read like f of t0 times g of t0 t1 up till tk plus f of t0 t1 times g t1 up till tk plus quite a few more terms plus f of t0 t1 up till tk minus 1 times g tk minus 1 tk plus f of t0 t1 up till tk times g tk. We had modeled ht as the truncated power function of degree k minus 1. Here the subscript represents the order of the truncated power function, and we had rewritten tj minus t truncated raised to k minus 1 as a product of two functions, namely tj minus t truncated raised to k minus 2 times tj minus t truncated. This expression here is h sub k minus 1 tj colon t, and this expression here is simply tj minus t truncated. We computed the divided difference of hk tj colon t using the Leibniz relationship. So hk t I minus k t I minus k plus 1 up till ti colon t, this is the kth divided difference, is equal to hk minus 1 of t I minus k t I minus k plus 1 up to t I minus 1 colon t plus hk minus 1 of t I minus k t I minus k plus 1 up till ti colon t times ti minus t. This is a result that we had seen in the previous lecture. So there are only two terms that get retained in the kth divided difference of hk. Those terms are the last but one term, which is this one here, and the last term, which is this one here. Since we are interested in the values of t in between ti minus k and ti, we drop the truncated sign here. We have seen this before. Continuing from here, if you look at this expression, this is the kth divided difference of truncated power function of order k. So this would be the B-spline m sub k sub I of t. K is the order, I is the index of the last knot. How about this expression here? This is the k minus 1th divide difference of truncated power function of order k minus 1. By a similar logic, this would be m sub k minus 1 sub I minus 1 of t. K minus 1 is the order of this basis spline, and I minus 1 is the last knot of this spline. How would this expression look like? Now notice here that this is the kth divide difference of order k minus 1 truncated power function. We do not know how this expression would look like. It is possible for us to express this relation in terms of two divide differences. Each one would be the k minus 1th divide difference. Okay, so hk minus 1 ti minus k up till ti colon t can be written as h of k minus 1 within square parenthesis ti minus k plus 1 going up till ti colon t minus hk minus 1 within parenthesis ti minus k plus 1 up to ti minus 1 colon t. Both of these are k minus 1 divide differences over ti minus ti minus k. This is this knot span here. Now, we continue with our discussion today on B-spline basis functions. This is lecture number 25. We'll also be discussing normalized B-splines and their properties. But first, let's revise the derivation of the B-spline mki as a function of t. So I have copied this expression from the previous slide. You know what this is? This is mki of t, and that is equal to mk minus 1 I minus 1 of t plus ti minus t over ti minus t I minus k times, we have seen what this is before. This is h k minus 1 square parenthesis t I minus k plus 1 up till ti colon t minus h k minus 1 square parenthesis t I minus k going up to ti minus 1 colon t. So mkit equals mk minus 1 I minus 1 t plus ti minus t over ti minus t I minus k times, now let's be careful here, this is the k minus 1th order spline mk minus 1, the last knot is ti, so we have an index I here corresponding to it, minus, again this is the k minus 1th order spline with the last knot ti minus 1. So the index here is I minus 1, and both of these are functions of t. I can rearrange the right hand side of this equation to club mk minus 1 I minus 1 t and mk minus 1 it. So this is how the final recursion relation looks like. mkit equals t minus ti minus k over ti minus ti minus k times mk minus 1 I minus 1 of t plus ti minus t over ti minus ti minus k times mk minus 1 I t. and this is an important expression that we are going to be using as a basis to study B-spline basis functions further. Many books start with this recursion relation or a similar one to discuss B-splines, the segments and the curves. I have gone through quite a few books and I always wondered as to where this expression comes from. The previous two lectures derive this expression, so we know where this relationship comes from. This looks a little complex in first go, but there is a very easy way for us to remember this expression. Let me explain this on the board. This is the way I remember to write the recursion relation for B-spline basis functions. Say I have to write the recursion relation for m sub k I of t. I know that this would be related to two B-spline basis functions of order k minus 1 each. Also, one of those basis functions will have the last knot as I, and the other one will have the last knot as I minus 1. So let me write them down. M k minus 1 comma I minus 1 t and m k minus 1 comma I t. Of course, there will be associated constants or weights with these basis functions. I'll fill them up in a while. Now first, the denominator. I come back to my parent basis function here. The last knot is ti and the first knot is ti minus k. I remember this and I use the entire knot span ti minus ti minus k here as well as here, ti minus ti minus k. Now the numerators. All I do here is replace ti by t, t minus ti minus k. So copy this expression here and let go of this index. How about the numerator here? I'll do the other way around. I'll copy this expression here and I'll let go of the index here. This will be ti minus t. It will take a little bit of practice for you to understand and remember this, but it is not very difficult. There is another interesting feature about this recursion relation. Now say that this weight is mu. It would not be very difficult for you to figure that this weight here will be 1 minus mu. An easy way to check this is add these two weights together. So we have the common denominator ti minus ti minus k. Here we have t minus ti minus k plus ti minus t. These two t's cancel out, So we have in the numerator ti minus k, which cancels with the denominator to give the result as 1. What do we notice here? This expression is very similar to the linear combination or the weighted linear combination we had seen in case of the de Castelnu's algorithm. Remember, we had studied that when discussing Bezier segments. So I've said this before, that this expression is very similar to that we have seen in the de Castelnu algorithm. This is like repeated linear interpolation between two consecutive splines. There is, however, a minor difference. In the de Castelnu algorithm, these weights were fixed for a given parameter value. However, here, depending on these knots ti and ti minus k, these weights get changed. We'll see this later. But because of this similarity, a table-like construction of B-spline basis functions is very much feasible. Let's look at that. So in the first column, we have the knot spans. The first knot span, ti minus k plus 1. The second knot span, ti minus k plus 1, ti minus k plus 2. The third one, ti minus k plus 2, ti minus k plus 3. The fourth, the fifth, and so on, up till this one here, ti minus 3 to ti minus 2, and then ti minus 2 to ti minus 1, and finally ti minus 1 to ti. We have to start with order 1 basis splines. M1 I minus k plus 1. Now concentrate on this knot here. This corresponds to the last knot in this interval. Likewise, the second one will be M1 I minus k plus 2. This knot here corresponds to this knot here on the right. And then M1 I minus k plus 3. Likewise, M1 I minus 2. Notice the correspondence here. M1 I minus 1, and finally M1 I. We can start performing linear interpolations from here on. Combine these two to get what? Of course, you'll get a spline of order 1 plus 1. How about the last knot over which the second order spline will stand? Take a look at this and this. Come back, take a look at these knot spans over here. This is the first knot span, this is the second knot span. So M2 something is expected to be standing over these two knot spans. The last knot will clearly be I minus k plus 2. M2 I minus k plus 2 of t. What happens when we combine these two order 1 basis functions? Again, there is an increase in order, and the last knot is I minus k plus 3. Okay, we can keep on moving. We combine these two guys together to get M2 I minus 1, which is this knot here, and M2I is obtained when we combine M1I minus 1 and M1I. there's another way to figure this last knot here. If we go back to the first column, we'll have to merge these two knot spans. And the last knot would correspond to the knot on the right of this merged knot span. We can keep working on the repeated linear interpolation, and eventually we'll get to the last but one stage, where we'll have two basis splines, m k minus 1 with the last knot I minus 1, and m k minus 1 with the last knot I. Now, if you look at this basis function, you would see that it would stand in the knot span given by these individual spans, ti minus k to ti minus 1. How would you check this? Simply subtract k minus 1 from I minus 1 to get the first knot, I minus k. The right index over here will automatically denote the rightmost knot, I minus 1. Likewise, for m k minus 1 I, this will be standing in the knot span given by this. The first knot will be t I minus k plus 1. The last knot will be ti. So as we move towards the right, constructing splines of higher order, these knot spans, they get merged one by one. Eventually, we'll get to mki, that will stand in the knot span ti minus k to ti. Not very difficult once you have a little bit of practice. Now, we have this recursion relation that allows us to construct m2, m3, m4, and so on up till mk. We will have to start, however, with the m1s. Do we have a recursion relation for m1? No. How do we then find what m1s are? Let's address this. What do you think the order 1 basis splines will look like? Let's use this observation that mki of t is non-zero in the knot span ti minus k to ti and is 0 elsewhere. The order 1 basis spline will be following the same rule or the same observation. So, m1I is non-zero only in one knot span, which is ti minus 1 to ti, and m1I is 0 for all the other values of t. Also, since the order of m1 is 1, the degree is 0. That would mean that m1I should be a constant in this knot interval, ti minus 1 to ti. What would that constant be? Well, we have seen this standardization condition before, and we can use that to compute m1I. Integral going from ti minus 1 to ti of m1I, a function of t dt, should be equal to 1 over 1. Since m1I is a constant, we can take this thing outside the integral sign. So this is m1I of t integration ti minus 1 to ti dt. This is m1it times ti minus ti minus 1, and this is equal to 1. So m1I of t is equal to 1 over ti minus ti minus 1. With this information here, the tabular construction that we had seen in the previous slide will work very well. Of course, m1I equals 1 over ti minus 1 for values of t belonging to ti minus 1 and ti. Notice here that I'm using the closed bracket on the left and an open bracket on the right. That will imply that ti will take the value ti minus 1, but not ti. And of course, m1I will be 0 for all other values of t. So the overall recursion relation looks like m1it equals 1 over ti minus 1 for values of t in between ti minus 1 and ti, close bracket on the left, open bracket on the right, and it's 0 for all other values of t. And then mkit equals, now you know how to remember this expression, t minus ti minus k over ti minus ti minus k times mk minus 1 I minus 1 of t plus ti minus t over ti minus ti minus k times mk minus 1 I t. This is for values of t in between closed ti minus k, comma ti open, and 0 for all other values of t. Now this index k can go from 2 to any value you want. Let's look at how these individual basis functions look like graphically. Let's take an example. Let's say we have the knots 0, 2, 5, 6, and 10. How many knot spans will they be? 1, 2, 3, and 4. What is the highest order of a B-spline basis function that can stand over this entire knot span? I would want you to guess that. Anyhow, let's start constructing order 1 basis splines. Let's number the knots T0, T1, T2, T3, and T4, or simply 0, 1, 2, 3, and 4. This is how M1, 1 will look like. The order M1 and the last knot, the second index. This value is 0.5. How is that so? M11 is 1 over 2 minus 0. How about the second first order spline? This would be M12. It is 1 over 5 minus 2. That is 0.3333 recurring. How about the third first order spline? Look at this orange line here. This is M1, 3. 1 over 1. This is M1, 4, which is 1 over 10 minus 6, 1 over 4.25. Notice that all these first order splines are constants in the respective t intervals. With these, let's now construct order 2 basis splines or degree 1 basis splines. Of course, geometrically, they're going to be looking like straight lines, inclined, that is. This curve here is M2, what is the second index? 2. And clearly it stands over the knot span 0 to 2, including the first two knot spans. As I said before, this is linear. Let me ask you this question. Would this function here satisfy the definition of a spline? Do you remember that? Well, the answer, of course, is yes. This is an order 2 spline, a degree 1 spline, and it has to be position continuous everywhere. Even though the slope here is not unique, you can see position continuity throughout. Why position continuous? It's Cn minus 2, where n is the order. So since the order is 2, it should be C0 continuous. Coming back to the second order spline. It stands between the knot span 1, 2 and 2, 3. Again, linear and C0 continuous. This is given by M2, 3. This is the third order 2 B-spline, M2, 4. Order the index of the last knot. Now let's start constructing order 3 basis splines. The first one will be a combination of M22 and M23. Clearly, the order is going to be raised by 1, and the last knot will be 3. So in this case, these two knot spans will get merged, and M33, which is this B-spline here, will be quadratic, C1 or slope continuous throughout. Notice that the slopes of M33 here and here are both 0. Coming to the second order 3 basis spline, that would be a combination of M23 and M24. The knot spans getting merged here will be from 2 to 6 and from 5 to 10. So M34, which is this red curve here, will stand over knot T1 and T4. And finally, one would combine M33 and M34 together to have order 4 basis spline, which is this bold red curve here. And of course, this spline is going to be standing over the entire knot span T0 to T4. Now this is interesting. Anyone would be able to practice this construction technique and understand how B-spline basis functions get constructed recursively. Now let's move on to normalized basis splines or B-splines. Of course, they happen to be more popular than MKI of T. The only difference between the normalized basis spline NKI of T and MKI of T is this factor here. In other words, you get a normalized basis spline by multiplying MKIT with the entire knot span over which this basis function stands, which which is ti minus ti minus k. Now we have seen this recursion relation before in terms of m's. Order k minus 1, order k minus 1. The last not I, the last not I minus 1, the last not I. You have also seen a little technique to remember this expression. Using this definition here, I can substitute for mki, mk minus 1, I minus 1, and mk minus 1, I. So mkit is nki of t over ti minus ti minus k. We use this relation here. How about m k minus 1 I minus 1? That is n k minus 1 I minus 1 of t over the last knot ti minus 1 minus the first knot t I minus 1 minus k minus 1, which is t I minus k here, plus ti minus t over ti minus ti minus k times n k minus 1 I over ti minus ti minus k plus 1. We can rearrange this relation as n kit equals t minus ti minus k over ti minus 1 minus ti minus k times n k minus 1 I minus 1 of t plus ti minus t over ti minus ti minus k plus 1 times n k minus 1 I t. Now, I find it personally a little difficult to remember this expression. If you can, it's wonderful. Just that I find it a little difficult. I find it more convenient to remember this expression here and to compute normalized basis line nki. All I do is I multiply mki by ti minus ti minus k. So the overall recursion relation for normalized basis lines. The first order normalized lines N1IT is equal to delta I such that delta I is equal to 1 for values of t belonging to closed ti minus 1 open ti, and N1IT is 0 elsewhere for all other values of t. And then for any other order, nkit equals t minus ti minus k over ti minus 1 minus ti minus k times nk minus 1 I minus 1 t plus ti minus t over ti minus ti minus k plus 1 times nk minus 1 I t. Before we proceed, a few comments on this recursion relation. To summarize, we have obtained this recursion relation using truncated power series function, using Newton's divide differences, and the associated Leibniz result. The second observation is with regard to computer coding. If you recall, we had gone through very tedious procedure to compute polynomial splines. In contrast, this is a much easier relation to work with when trying to code to compute B-spline basis functions, where the normalized or not normalized. I have always been emphasizing that it's a nice idea for us to be comfortable in constructing or sketching these B-spline basis functions geometrically. The reason is very simple. It will help us understand the properties of normalized B-spline basis functions better if we are adept in sketching these functions. In that regard, let me leave you with a few questions for you to mull on. Question 1. Sketch all intermediate and final results for the normalized spline N6IT. Remember that the sketching procedure for N6 sub IT or any other normalized basis function is identical to that of the corresponding MKIT. You do not want to worry about the magnitude while you're sketching these B-spline basis functions. Question 2. Sketch all order 4 normalized B-splines in the knot span Ti minus 10 to Ti. We would only need the final results here. We don't need to worry about the intermediate B-spline basis functions. Question 3. Play with different order normalized B-splines over the span T minus I minus 8 till Ti plus 4. Nomenclate or identify each B-spline after sketching them. To make matters simple, try order 4 5, and 6. Question 4. In question 2, think about what will happen if the knots T I minus 5, T I minus 4, T I minus 3 get merged. So remember here that not all order 4 normalized splines will get affected when a few knots get merged here. Also, you can simulate the merging either from the right or from the left. What do I mean? You can do so in steps. You can first say Ti minus 4 equals Ti minus 3, and then Ti minus 5 is equal to Ti minus 3. Or you can merge these knots from the right by saying that Ti minus 4 equals Ti minus 5, and then Ti minus 3 equals Ti minus 5. In the next lecture, we are going to be studying the properties of the normalized B-spline basis function.